So, we had started with one consistent set of propositions sigma, then we could extend it to sigma prime, which we proved to be maximally consistent. So, this fact that a consistent set can be extended to a maximally consistent set is called Lindenbaum lemma. So, that may not happen in every system, in this system it happens. So, that means Lindenbaum lemma holds in PC. So, next we had proved some of the properties of sigma prime, this maximally consistent set, which essentially captures the connectives. So, those last four properties, one for negation that either P or not P belongs to sigma prime for any proposition P, and then the other three for the implications. So, those properties, if a set holds, in a set if those four properties hold, then we would say that that set is a Hintikka set. So, there are many technicalities there. So, that means we have proved that there exists a Hintikka set, which happens to be our maximally consistent set sigma prime. So, we are almost over in proving the completeness of PC. So, our formulation was if sigma is consistent, then it should be satisfiable, right. Okay. So, what about sigma prime? Sigma prime is consistent. Can we show that it is satisfiable? In fact, that is the technique, that is why we had extended sigma to sigma prime. And that sentence, that statement which says that if sigma is consistent, it is also satisfiable, is called model existence theorem. There exists a model for a consistent set. Okay. So, this is what we want to derive next. So, this says if sigma is consistent, then it has a model. I will say that then sigma is satisfiable. So, its proof is easy now. What we have to do is find a model for sigma. Okay. So, now here only we are connecting PC to PL. Consistency is a PC concept, it is coming out of the proofs, definition of proofs, and satisfiability from the semantics, truth and falsity, there we are connecting now. So, what we do is let sigma be consistent, then consider sigma prime. Now, sigma prime is maximally consistent, and it along with it satisfies all those properties. Now, what happens? You define one function, define some function I from the set of all propositions. So, now in the set of all propositions we do not have those connectives and or if and only if, and then we do not have top and bottom also, right. There is not these symbols in PC, that is our set of prop now, which is appropriate to PC. So, define from this set to 0 1 a function by taking I of any proposition say u equal to 1 if u belongs to sigma prime, it is 0 otherwise. Okay. Now, is it not obvious that this I is a model of sigma prime? It is, because by definition it is 1, but we have to verify that it is really a Boolean valuation. It is a function, that is fine, but it has to be a Boolean valuation in order that it is a model. That is why we have done all this work. Okay. Now, it should be obvious that it is also a Boolean valuation because of those four properties. If you take any proposition u, either u is in sigma prime or not u is in sigma prime, right. So, either it is given 1 or it is given 0 with respect to the negative sign, negation sign. And what about other properties? The other three properties capture the implications, right. If q belongs to sigma prime, that is if I of q equal to 1, then P implies Q belongs to sigma prime. So, I of P implies Q equal to 1, right. That is first property of implication. Next you have if not P belongs to sigma prime, that is if P is given the truth value 0, then P implies Q is also given the truth value 1, it belongs to sigma prime, right. That is the next property of implication. Then you see that if P is true, Q is false, that is if P belongs to sigma prime and Q does not belong to sigma prime, then P implies Q should be false, that is also true. P implies Q does not belong to sigma prime, that is your last property, right. So, now we just see from this that I is a Boolean valuation. Due to last 4 properties. What are they? 5 to 8, right, of sigma prime. Now, that is all, that is the end of the proof, right. So, I is a model of sigma prime and sigma is a subset of sigma prime. So, I is a model of sigma, right. I satisfies sigma prime, sigma is a subset of sigma prime. So, I is a model of sigma. So, easy consequence now. Once you did sigma prime, there is nothing to prove, and thereby we have also proved adequacy of PC to PL is in fact strong adequacy, right. So, let us mention that. So, adequacy really means what? Sigma entails W if and only if sigma semantically entails W. This is your strong adequacy, and if you do not have strongness, you say W is a theorem if and only if W is valid without any sigmas, right. So, proof is easy because this holds if and only if sigma union not W is inconsistent, okay, and this holds if and only if sigma union not W is unsatisfiable, and now consistency and satisfiability are on par, right. Model existence theorem says one part, soundness theorem says the other part, right. In fact, adequacy means soundness plus completeness, both the things are there. Is that clear? So, there is a nice consequence of it. So, it says something like you start with one infinite set, okay. Now, suppose that it is unsatisfiable, then you can show that there exists a finite subset of it which is unsatisfiable. That is what compactness means, right, which means same construction will prove it, but we do not have to prove it once more because we have adequacy, right, and in PC we have finiteness. So, immediately you can jump. So, if you want to see what this says, it looks simple now after all this, but it is not a very simple concept. Suppose you start with one infinite set, right, infinite set of propositions. Now, you take all its finite subsets, right. Suppose we claim that each of the finite subsets has a model, right. Can you construct a model for the whole infinite set? This is the problem. Do you see it? See, as a particular case, suppose you have sigma which have W1, W2, W3 and so on. Now, for W1 you have a model, for W1, W2 you have a model, W1, W2, W3 also have a model and so on, right. but not only this, we are assuming something more, we are assuming every finite subset of it has a model. Now, how to construct a model for the whole set? The clue is, when you say that every finite set subset has a model, it is not necessarily the same model, it is not the same I, right. It can be different I, it need not be an extension from a subset to a superset of it, it can be completely different. Still from that you can always construct one model for the whole infinite set, that is what compactness says, right. So, let us write that compactness for PL. This is, let sigma be an infinite set if each finite set of sigma is satisfiable, then sigma is satisfiable. So, now proof is easy. What you have to say is proof its contraposition. If sigma is unsatisfiable, then there exists a finite subset of sigma which is unsatisfiable. Okay? Which finite subset we do not know, but we can show there exists one. So, suppose sigma is unsatisfiable, then by strong completeness theorem or model existence, whatever you take, we want only completeness here. You see that sigma is also consistent. Now, you are trading between PL and PC. So, if sigma is satisfiable, then sigma is also consistent, right. Similarly, if sigma is unsatisfiable, it is also inconsistent. Okay. Now, suppose sigma is inconsistent. So, that means sigma entails P, sigma entails not P for some proposition P. Okay. Now, again you trade between PC and PL. You say sigma semantically entails P, sigma semantically entails not P. Okay. But wait a bit, from the PC itself, when you say it entails, you have a proof of it, right, but that proof contains only a finite number of propositions. Okay. So, both the proofs have only finite number of propositions each. So, their union is also a finite subset of sigma. Now, you concentrate on that finite subset and trade between PC and PL. So, call that sigma 0, which is union of all the premises used in both the proofs, right, or either of the proofs rather, right. You have to take the union. Then sigma 0 entails P, sigma 0 entails not P semantically. Sigma 0 is unsatisfiable, that is the proof. Clear? See, all the properties are not compact properties, that is why it becomes non-trivial. For example, suppose in natural numbers, you take any finite subset of natural numbers, you will have a maximum, right, but the whole set natural number does not have a maximum. Okay. So, taking maximum is not a compact property, but here it is, satisfiability is a compact property, that is what it says. Okay. That is why it becomes non-trivial, though in PC it is very trivial, because our definition is through a finiteness property, a proof is a finite sequence. So, that is why when you say PC and PL are adequate, it gives some more information. It is not just I have started with some axioms and proved it. Okay. Fine, if we get some time, we will do some applications of compactness. Right now, we will not. We will resist the temptation. Okay. See, in PC, what happens? We are looking at the proofs now. Construction of proof is not effective, as we have seen, right, but we have not proved it, why it is not effective. All that we have seen from our experience, that the idea of proof, notion of proof is effective. You can always check whether some sequence of proposition is a proof or not, but how to construct a proof depends on your cunningness, right. It is not mechanical. Okay. can we have a mechanical method, something like that. Resolution was somewhat mechanical, fine, but you need a CNF conversion, that is again mechanical. So, there is a hope mechanically something can be done, right, and it is mechanical from the beginning. Suppose you have a finite set of propositions, you can always find out whether it is consistent or inconsistent mechanically by a very crude procedure, construct its truth table, right. It is very long, it does not matter, there exists a method. Okay. So, that concept is called decidability of a theory. So, in propositional logic the thing is decidable, whether something is consistent or inconsistent is decidable, provided you have a finite set. Okay. For infinite sets you do not know what to do. Okay. Now, we will see that there are still some other methods which can be very easy, and we will present one such method. In fact, the method is so easy and so intuitive, at the same time it is so formal that logicians become addicted to it. Once you say whether this is consistent or not, immediately they will go for that. Okay. Yes, we will see why is it so. It is very simple observation. Suppose I take P and Q, one proposition. Now, how do I decide whether this is true or false? Well, first thing is P and Q is true if both of them are true, right. So, I just construct a tree. If P and Q both are true, then P and Q will be true. Okay. Suppose I take P or Q, a similar construction, P or Q will be true if at least one of them is true, right. So, I have now two cases, just the way we did from our childhood. Okay, there are two cases, one of the cases will succeed, then I say that P or Q is true, fine. So, I will branch into two parts P, Q, I just keep it. I do not know what will happen to this P or Q, but this can happen, right. So, this gives a method how to proceed, but this says that preliminary conversion is required for and or. Okay. But we will not do that way. What we will do is we will try to identify the forms of propositions. Propositions can be in which form? Suppose all the connectives are used, then let us see what can be the forms of the propositions. Okay. This is required because by De Morgan, say I have not of P and Q. Though I know P and Q is true, when both of them are true I can make a tree with both P and Q in the same path, right. But if it is not P and Q, I know it is equivalent to not P or not Q. Now, if it is equivalent to not P or not Q, then I should have branched out with one as not P, another as not Q, which says not of P and Q is true if one of this is true. Okay. So, now you see, even if and is there, because of negation sign, some proposition can be just and of something or negation of ands of something. Similarly, from each connective, other 4 connectives, you will get 8 such cases, right. A proposition can be in that form or negation of that form. Is it okay? And then we have top and bottom, so you have to do something for that. We have double negation, so it can be not, many nots can be there, right. So, recursively we should have a rule for not also, fine. So, this is expanding propositions in such a fashion is called a tabula. You go on finding the table, how it is going, finding out the cases when it can be true and so on. So, these types of trees are called Betz semantic trees. So, semantically we are just computing a tree, making a tree, finding out what are the possibilities when it can be true, right. Proposition at the root can be true when, that is what the trees answer. These trees have been modified to make a proof method, that is what we are going to present. Okay. So, this tabula will have certain rules basing on the forms of the propositions. So, I will just write the rules first, let us see. So, we will have rules of this form. If it is in the form not, you get P. Again we will write in this fashion, fractions. So, this means if not P is there, this will be true if P is true, semantically it looks like that. But when you construct a true proof system, it can be semantically motivated, but there is no trace of semantics there, right. It is mechanical, that is what we want to make, just like your PC. So, we will just construct them as rules now, think of them as rules, forgetting the semantics. Whenever needed, we will connect them, right. So, now if it is in the form not top, we can write bottom. Okay. Now, if it is P and Q, we will have P, we will have also Q. Okay. If it is not of P and Q, then we will have two children, one is not P, another is not Q. Okay. If it is P or Q, we have again two children. Okay. This can be written as a fraction, we just write this way. Okay. When you construct the tabula, we will be connecting by trees. Then P or Q, we will have P as one child, Q as the other child, right. See, if you do not like the fractions, you can simply connect by vertical bars or slanted bars, does not matter. Next, we have not of P or Q, which will be not P, not Q, both are in the same path, right. Next, we may have P implies Q, which will have again two children, one is not P, another is Q. See the semantics, P implies Q is equivalent to not P or Q. Next, you have not of P implies Q, which is equivalent to P and not Q, right. So, we will have P not Q in the same path. Next, if and only if P by conditional Q, this is true when both of them are true or both of them are false. So, we will keep in one branch P Q both, another branch not P not Q. Okay. The negation of P if and only if Q, so that is equivalent to either P or Q, right, exclusive OR. Okay. So, this is true when one is true, the other is false. So, that gives rise to P not Q, not P Q. These are all the tabular rules. Any proposition can be in these forms, or there can be another form like bottom only. So, you have to give somewhere this rule, you have to take care of that, how only bottom can be handled. Okay. That is only missing here. Fine. Now, as it says, as our heuristic says, if a proposition is given, we are going to apply the tabular rules and then branch out, construct the tree. So, construct the tree as big as you can, as far as you can go, continue. After the construction, what are you going to decide, right? That is the point where we have to write something about the rule, how to use the rules, that we know now for the construction of the tree, for the expansion. Then after you expand, what are you going to decide? Well, it is also easy. For example, I take P and not P, I know this is to be unsatisfiable, fine. Now, for the tabular rule, it gives me P not P both, right. So, semantically it says, in order that this will be true, this will be evaluated to 1, both P and not P should be evaluated to 1, which is not possible, right. So, as a child, if it is not possible, I will cross it, right, it is not possible. So, this is what we are going to introduce in the tabula. If in a path, in a tabula, you find that there are two complementary pair of literals, there is a pair of complementary literals, then you close that path with a cross, right, provided you have applied the tabular rules on every situation wherever it is applicable, then you will end in literals, but you may not end in literals. If you end in a proposition P and also its negation, it is also fine, whatever way you expand, they will close, right. Is that clear? For example, let us see, say I have P or Q and not of P or Q. Okay. Then once I apply the tabular rule, it will give me P or Q and again not of P or Q. Okay. Now not of P or Q gives me not P, not Q, okay, and P or Q gives me P, Q as different children. Okay. Now I see the path. The path you can see either from a root to leaf or from leaf to root, does not matter. Let us take root to leaf as usual. So in this path I see that P is there, not P is there, so this path closes. Okay. In the other path I see not Q is there, Q is there, so that also closes. Now the question is, why should I go this far? I have already got a proposition U and not U. So whatever way I expand, they will close, right. So this is the shortcut we will be going to make. Instead of going to the level of literals, whenever you find a proposition and its negation, stop there, close the branch. Is it okay? So why we did not have a rule for the bottom? This is what we are going to write. If you find in a path a proposition or its negation, you close it, or if you find in a path bottom is occurring, close it, because that will tell you that in order that the propositions in that path are true, bottom should be true, it can never be. So that path also closes, right. So there we are tackling this bottom, all others are given the rules. So our rule will be, if in a path you get a proposition, its negation, okay, that is one case. Second case is, if you find a bottom, then close the path. Okay. So now suppose you take a proposition and construct a tabula for it using the tabular rule. You see that every path closes, then what do you conclude? It is unsatisfiable, right. If every path does not close, see, from the beginning itself I could have told P and not P is satisfiable, I do not expand it, right, I become lazy. P and not P, I do not expand it, I keep there. Okay. Now this is also a tabula by definition, it is open, it is not closed, so it should be satisfiable, but that is not the case, right. So that means to take a decision that one open path really gives rise to a model which will make it satisfiable, right. You have to see that all the compound propositions have been expanded. So compound means all those propositions in the forms of the numerators in our rules, right, they are the compound propositions. So you should have applied a rule on the compound propositions in that path. If it is done, still the tabula remains open, then it will be satisfiable, right. So we have to make certain definitions for all these situations, to take care of the situations, then it can start, fine. So let us give a definition, whatever we need here. First thing is, you have the tabular rules, then you have to say how to expand the tabula. Okay. So there a proposition at the root of a tabula can give rise to a tabula. So this is a cryptically written. It says start from a proposition, then apply the rules if it is compound and continue. That is what it says recursively, right. But then there is one simple caution there. The caution is this, just look at the tabula we have constructed here. From the third proposition we got to not P and not Q. Instead of the third, suppose I go for the second. So, what will happen? I have P or Q, I have not of P or Q. Now, I first apply OR rule. Okay. So, I would get P, another as Q. Now, I want to apply this. See that is the point, right. That is a subtle point while you are completing the going for the tabular expansion. Once you take one proposition at the top level which is beyond all these branchings and you want to apply tabular rule on that, then you have to add on every leaf, right, because tabula are expanded pathwise. We have to concentrate on each path, because we are going for a construction of a model along that line, right. So, in programming it can be easy, because you can expand all these things pathwise, continue. If it does not close, you stop there. If it closes, you backtrack, right. That can be done, but while doing it manually, usually you apply it breadth first way, not this way pathwise. So, once you do breadth first way, be careful about that. If you apply a rule, you will think that I have already applied, but that is guaranteed if you have added in every branch, right. So, once this has been used, let us take it. I have not used it. To use this, I have to add not P, not Q in both the branches. This is what it says. Now, you can see all the paths will be the same literals here, same literals also here. Is it clear? Okay. So, now you have to define all these things formally. So, a tabula is expanded or is constructed pathwise. In a path, rules are applied on the compound propositions. So, in this sense, the tabular rules are really tabular expansion rules. How to expand the tabula, right? So, that is how it is constructed throughout. Sometimes you need not have to construct the whole tabula. Somewhere you find P and not P is there for some proposition, you close it. So, there is no need to go further, right. But if you want to go further, then we should give a name for that kind of tabula, right. So, you say that a path is, so path means path from root to leaf, wherever you are now, what is your leaf, current leaf. So, path is called closed if it contains P and also not P for some proposition P, or it contains bottom. Otherwise, we say the path is open. So, this open and closed, they are dynamic. Up to some level, a path can be open, but once you apply another, so one of its paths can be closed, right. Even both of them can become closed later, right. So, it is a dynamic thing. A path is called complete, if it can no more be expanded, right. So, that means on each of the compound propositions occurring in that path, a rule has been applied, right. So, if on each compound proposition occurring in that path, a tabula expansion rule has been applied. See, sometimes you say I do not have to complete the path, I can take decision before it. Okay. So, we will also include one term for that. We will say that a path is completed if it is closed or it is complete. So, that means it is essentially complete, right, nothing can be done for it. You know it is closed, you have decided for it, or it remains open, nothing more can be done by using the tabula expansion rules. So, in fact, we wanted this completed path to take any decision, right. Then we come for the tabula itself. Okay, let us leave it here. Okay. A tabula is closed if all its paths are closed. This is what should give us one unsatisfiable proposition at the root. Okay. Similarly, we say a tabula is complete if all its paths are complete, not one, complete. Everywhere compound propositions have been resolved, right, they have been expanded. And similarly, we say tabula is completed if all its paths are completed, right. So, closed or complete or completed. All these go. Now, comes the next one. A tabula is open if here you require that, if at least one of its paths is open, not every, right. You do not need every, right. If at least one of its paths is open. Okay. So, for taking decision whether it is satisfiable, you may need an open completed tabula, right. It should be completed. If it is not complete, but only open, your decision cannot be taken. It can still be further expanded and found to be closed. Okay. So, you need a completed tabula for that. Then we should define the syntactic part of all those things. We cannot say satisfiable or unsatisfiable here, because it has nothing to do with the truth or falsity, though it is semantically motivated, but as a proof system it may not have any semantic content. Fine. So, a tabula for a proposition W is a tabula with root as W. So, you have to define everything almost. So, once you say a tabula for a proposition, that means you start the tabula with the root as W, then continue expanding it. Fine. Similarly, you can say a tabula for a set of propositions say sigma is a tabula with all propositions of sigma at the root. Okay. Now, we define a theorem, a tabula theorem, or we say propositional tabula. okay, PT for propositional tabula is a, okay, we can say what is a PT. We start with a proposition we say W is a PT theorem if what happens, if there exists a closed tabula for not W. Now, you see reductio ad absurdum is inbuilt in the definition. Okay. You start with not W, then expand it, find that tabula closes. See, a tabula may not be unique, it depends on which order you are using the rules, it can become very different. Okay. So, all that you need is there exists a closed tabula, fine. Then similarly, for a set of propositions, we say that sigma is inconsistent. In fact, you should write PT inconsistent. Okay. Inconsistent in the system PT if there exists a closed tabula for sigma. Okay. Start with all the propositions at the root and then continue using tabula expansion rules, see that closes. If it closes, you say that it is inconsistent. Okay. Now, similarly, you say sigma entails in PT W right. So, if sigma union not W is inconsistent, PT inconsistent, right. So, inconsistent here means PT. So, slowly, since you have become matured, we will forget this PT always writing, we will say inconsistent or theorem and so on. Once we are in the context of tabula, it will be interpreted as tabula consistence, not PC consistent. Okay, let us see one example at least, how to show something is inconsistent or not. Okay. So, let us see whether this happens or not. In fact, you should have PT here, right, as a subscript. In PT only we are deciding. So, that means sometimes we will say that sigma entails W has a tabula proof, okay, that is also used. Now, how to proceed? We simply start with sigma union not W. Okay. So, P implies not Q implies R, P implies not Q, not of P implies R. So, often we write independent propositions vertically, because we want to apply the rules, right. So, they will be on the same path. So, it is more logical to start with vertical things, then comma and then write it. Okay, now, you have to apply the rules. See, I want to apply rule on this first. Why? If I start from this, then it will branch out from the beginning. Okay. Then every branch I have to add this. If I start with this one, it will be stacking, it is not branching. So, it will be helpful. Okay. So, in all those rules, wherever you get two children, they are called the branching rules, others are called the stacking rules. they are just stacking the propositions one after another, the other ones are branching out. So, now it is helpful as a heuristic that if there is a choice, go for the stacking rules instead of the branching rules, okay? That will make the tabula shorter. So, now if I apply not implies rule, we can give a name to all the rules now. Let us call this rule as not, because that is the form of the proposition we will be meeting. This one will be not top, this is and, this is not and, this is or, this is not or. Similarly, this is implies, this is not implies, this is biconditional, this is not biconditional. That says the form of the proposition directly also. Now, if I apply not implies rule, it gives me P not R. Is that right? Next, which one? Well, I can go middle one instead of this, that will again branch out. So, this gives implies rule I use, that gives what? So, it is often easier for you if you go on a bookkeeping device. See, once I use this, I tick it, okay. It will not come further. Then what about P implies not Q? It will branch out to not P, not Q, okay. Now, I close it, instead of applying this, I will close it here, because I have already got P and not P in this path. So, I close it, and on this not Q, the other path not Q, not R, P and so on, I have one on which I have not applied a rule, right, tabular expansion rule. So, this I have to apply implies rule. So, that gives me not P and then not Q implies R, okay. Again in this path I find not P, not Q, not R, P, okay. So, P and not P are there. So, that path also closes. Then I look at not Q implies R, all the things have been used. In this path there is another compound proposition where I have not used the rule. So, I branch out to not Q and R, okay. If you use double negation, it will go to Q, but I do not need that. I have not Q here, not Q here. You can further take Q, but does not matter. So, that also closes, and here not R and R, they also close, okay. So, it is closed. Therefore, the set of propositions is inconsistent, but we do not have to say that, we just say this is proved by tabular method, because our definition says if there is a closed tabula for all sigma and not W, that we have taken directly, okay. Now, as an exercise you can try all the axioms of PC and MP also, okay. See how do they go in tabular rules. So, slowly you should get acquainted with this, very quickly you can decide what happens, that helps. So, today only we have done tabula, no, we have done also completeness of PC and compactness, right, and then the tabular rules. So, we will discuss again tabulas next time maybe.